All right, guys. So I bet you remember our motion unit and that big old packet that we had. Now we're going to take a little visit back to it and how we can apply integration and antiderivatives to that motion. So we had a couple of conversations during that unit of how do we go backwards? If they told me about velocity, how am I supposed to go back and know anything about displacement? Well, this is how we do it. So here's a few things I want to remind you about. S of t, that function is our displacement. V of t is velocity, and that's the derivative of displacement. A of t is acceleration, so that's the second derivative of displacement, or the first derivative of velocity, however you want to look at it. Now, there are two different things that we'll have to find using integration. The first is change in displacement. So remember, displacement is whatever distance you are from some sort of origin. So you might be, you might start off at 3 and end up at -2. And so your change in displacement is -5. But maybe during that time from 3 to -2, you went up to 5, down to -8, up to a billion, down to 70 million, back up to, you know what I'm saying, right? So to get that total distance traveled during that time, we take the absolute value. So the change in displacement from one time to another, like if we were to take a snapshot, this person is standing here at time t1 and is standing here at time t2. Here's the difference in those two places. Total distance traveled, when we have that absolute value on our velocity function, that's going to tell me how far did I actually go. So think about running a race. So if you go around the track once, your change in displacement might be 0, or it might be -1 because you're still trying to make it there. You didn't, you know what I'm saying? But the total distance traveled is the full distance around there. So the reason we want to use absolute value is because this change in displacement, some of them will be negative, some of them will be positive, and they'll just kind of cancel each other out as we go down. When we have the absolute value, that will make sure that nothing cancels each other out, that all of the distances are accounted for. So the displacement function for a particle moving along a horizontal line is given by S of t equals 8 plus 2t minus t squared, for t is greater than or equal to 0, where t is in seconds, and S is in meters, spelled the British way. Okay. Find the velocity at time t. So basically what they're asking for in this is just, what's the velocity function? Remember, to find the velocity function, we want to take the derivative of our displacement function. All right. So our function was this 8 plus 2t minus t squared. So we need to take the derivative. Now remember to keep stuff straight, because we're going back to derivatives after doing integrals for so long. So it can get a little bit confusing when you're going back and forth, but you'll get used to it. So the derivative of 8 is 0. The derivative of 2t is 2 minus, multiply by the power, subtract the power by 1. So we have 2 minus 2t for our velocity at time t. So now we want to find, when is the particle moving to the left, or when is the particle moving to the right? So here's what we should be thinking for left or right. If the particle is moving to the left, that means that the displacement is decreasing. If the displacement is decreasing, that means that the velocity is negative. Conversely, to the right, that means that my displacement is increasing. And if my displacement is increasing, that means that my velocity is positive. So how do I know where velocity is positive or negative? We want to go ahead and make a sign chart. So remember, my t values start at 0. So I'm not going to have a line with arrowheads on either side. This is going to be more of a ray situation. There we go. Okay, so what we want to do is take our velocity function and set that equal to 0. So 0 equals 2 minus 2t. And then we should go ahead and solve for t. So we'll add 2t to both sides. Divide by 2. So t equals 1. So I think my function will change direction after 1 second. So what we want to do to find out is my velocity positive or negative during these times is go ahead and plug some stuff in. So right here, let's plug in a half, maybe. So 2 minus, and then 2 times a half is 1. 2 minus 1 is positive. Good deal. So since my velocity is positive there, that means that my particle is moving to the right. And then we'll plug in something on the other side. So we can plug in 2, we can plug in 80. Let's do 100, okay? So 2 minus 2 times 100. 2 minus 200 is definitely a negative number. So since I have a negative velocity over on this side, that means that my particle is moving to the left during this time. So we want to make sure that we write out our answer in a way that makes sense, not just throw it out there in a diagram. So we are moving to the right. From 0 until 1. Notice I didn't put or equal to. At 0, we weren't necessarily moving. We don't know what was happening then. And at 1, we were changing directions, so we weren't moving to the right or to the left. So that's not or equal to. We want to make sure that's an open interval, no or equal to's. And then we're moving to the left the rest of the time. So that's from where t is greater than 1. Or you can write that out in words if that would make you happier. Moves to the right from until 1 second, then moves to the left from then after. Whatever works for you. As long as you are communicating in a way that makes sense, you're pretty much fine. There's no necessary notation that you have to use. Okay. So we want to write a definite integral, 2 definite integrals, to find the particle's change in displacement and total distance traveled from 0 to 4, and then solve. So if you remember from just before this, we had our integral to find the displacement from A to B. So in this case, our A is 0 and our B is 4, or T1 is 0 and T2 is 4. And then for the displacement, we're supposed to use the velocity function right there. So if we look back, our velocity function for this problem was 2 minus 2t. So I'm going to take the integral from 0 to 4 of 2 minus 2t dt. Good deal. Now for the total distance traveled, the only difference between these two is that this one had an absolute value on it. So it's the same thing, the integral from 0 till 4, but now I want the absolute value of 2 minus 2t dt. Good deal. Now we want to solve. So my advice is to go through and actually use your calculator on this one. So on this first one, remember, we're going to Okay, so to find these integrals, we're going to use our calculators. So we're going to click math, and then 9, and then we'll put from 0 to 4 of 2 minus 2x dx, and press enter. So displacement, we end up with -8, and that would be meters, or 8 meters left if you want to use directions. Now that one we absolutely could have done by hand, but why waste the brain power when we have, all of this fun stuff to help us out? Now the absolute value, I don't know how you would do that without a calculator, honestly. Here's what we're going to do. So one more time, math 9. From 0 until 4. And now we have to get absolute value in there, right? Oopsies, I put a 25. Yikes. So to get absolute value, what you want to do is click on math, and then go over one to num, and up on the top is abs. That's what you want. Abs is absolute value. So we'll press enter. Absolute value of 2 minus 2x boop, boop, dx, and press enter. And this time we ended up with 10. So the total distance traveled was 10 meters. Good deal. So what happens when you have a graph? Well, actually, it's even easier. So there we go. The velocity function v in meters per second of a particle moving along a line is shown in this graph right here. Find the change in displacement and the total distance traveled. So, first of all, let's have a conversation about what the heck is an integral. If you remember at the very beginning of the unit, we went and found areas of each of these sections right here, and that would help us find out what the integral was, right? Because finding an integral is the area underneath the curve. So that's what we want to do right now. That's how I'm going to start. I'll address which one is which here in a little bit. So over here we have a little triangle right here. Remember, triangle is base times height divided by 2. The base of this triangle right here is 4. The height of my right triangle right here is 4. So then 4 times 4 is 16, divided by 2 is 8. So I know the area of this triangle right here is 8. Then we have this triangle over here. Once again, we know that the area of a triangle is base times height divided by 2. The base of that triangle, let's see, 2, 4, 6, 8. And the height of that triangle right here is 4. So 8 times 4 divided by 2 gives me 16. All right. Now this section down here, you have a couple of different options. If you're comfortable with finding the area of a trapezoid, which is what I'm going to do, cool. Some of you might want to find the area of this triangle, the area of this triangle, and then you have these two little blocks inside of there, add it all together to get the area of that thing. Whatever works out. I'm going to find the area of my trapezium, though, because we're in IB, so it's a trapezium. So remember, to find that area, we add the bases together, we multiply it by the height, and then we divide that whole thing by 2. So one of my bases down here, this bottom guy, is 1. And then I have from 12 to 16 is 1, 2, 3, 4 units. And then the height right here we can see is 2. All right. So 1 plus 4 is 5. Times 2 divided by 2 leaves me with 5. So far we have all of our areas. We are 90% of the way there. Now we have to interpret these answers and apply them to our situation. So we want to find the change in displacement. I'm actually going to put change in displacement as change in displacement. Cool. Okay. So remember, we're not worried about absolute value with this one. If I have an area underneath the x-axis, that needs to be negative because that means my particle is moving to the left. Over the x-axis means my particle is moving to the right. So here we go. Below the x-axis, it's -8. 16 is above the x-axis, so that's positive. And then 5 is below the x-axis, so that's negative. So when we total that all together, the total change in displacement for this particle from 0 to 16 is 3 meters. But now the total distance traveled, it doesn't matter which direction we were going in. Everything is positive here. So I'll take that 8, add that to my 16, and then add that to my 5. So the total distance traveled was 29 meters. Good deal. So we are all done with this unit. Pretty exciting, right? I'm excited too. So I'm going to teach you a few more things about binomial distribution. We'll review for the rest of this, for the rest of the week. Then we'll do some binomial distribution. It'll be great. Okay. I miss you. I love you. See you guys later.